Today we'll be working on the following problem. Let X be a complete metric space. G be a non-empty open subset of X. We want to show that G is non-meager. So pause the video if you want to work on this problem by yourself. Okay, let's see what is our proof. So basically, we have this complete metric space X, and the G is a non-empty open set. So we want to prove like G must be non-meager. So usually when you have a complete metric space and then you want to prove some set is meager or non-meager, dense or, stuff like that, the bare category theorem is a great tool, right? So here in this case, let's see how we can leverage that bare category theorem, right? So let's say suppose that G is meager. So we want to prove by contradiction. Suppose G is meager. So by definition, G is the countable union of lower dense set, right? So let's see, G is the union of E sub n, and then each E sub n is nowhere dense. In other words, the interior of E sub n, the closure is empty, right? So let's see, because clearly we can see, G is contained in the union of the closure of E sub n, right? Because each E sub n is clearly a subset of the closure of E sub n. So G is contained in here. So now the complement of G, which is, this is just the complement of the G, right? So the complement, it is containing the complement of this. Complement, right? And now use the distribution of this, so the union becomes intersection, and from 1 to infinity, the closure of E sub n, and then take complement, right? So this is just 1 to infinity x minus this, right? So now let's see for each, now we have the, this is the intersection of all of this, right? So now, because the closure of E sub n is closed set, so x minus the closed set. So let's see what is the closure of this. So we can see the closure, this one, and then we take the closure, right? This is a closed set. So the complement of a closed set take closure. This is the same as the complement of the interior of this from our problem, the previous problem, 36, part 8, right? So we have this. And now by assumption, the interior of the closure of E sub n is empty because E sub n is nowhere dense. So this is actually empty set. And then x minus the empty set, the complement, of course, is x itself, right? So now what do we have? So now for each x minus E sub n the closure. This is open. Alright? Because this closed, the complement is open. And the closure is X, the entire space. So that's, this is open and dense in X for each n, right? So we have a series, a sequence of open, dense subset of X. So by Barry's category theorem, the intersection of all of them is also dense. The intersection of this n is also dense in X, right? That's by the theorem. You have a sequence of the intersection of open dense set is also dense because X is complete metric space, right? So, but then here we have the complement of G contains this dense set, right? So is also dense, which means G complement is also dense in X. But this is impossible, right? Why is it impossible? Since G is non-empty. Right? You have this non-empty G and this X. So you have the complement is dense, cannot be dense in X, right? So you have this like a hole, a non-empty hole, which since it's impossible. So therefore our assumption is wrong, right? What we assumed is G is meager, so the meager it's wrong. So therefore G is non-meager.